I want to start working on inverse trigonometric functions, but let's just discuss first just inverse functions, inverse relations in general, and then we'll take it from there. What is a function? Does anyone recall? We probably discussed it when we defined the trig functions. What's a function? That's all right. What's a relation? A relation is an assignment between elements of a set called domain and another set called range. That's not a function. For example, why isn't it a function? Because you can take one element of the domain and assign multiple values to it. That's not allowed in a function. A function has that restriction, just one value to be assigned. For example, you can have more than one phone numbers, more than one addresses. Anything you can have more than one, that assignment is not a function. Function is a special case of a relation when we insist that only one thing can be assigned to each element of the domain. So it's that single assignment. And it's a reasonable request, especially when the domain is time. At a certain point, you just have one location, one temperature, one grade point average, one value of a star, and so on. So a function is a relation. So it has all the ingredients of a relation. It has a set called domain. It has a set called the range. And it has an assignment between elements of the domain and the range. And in addition, there is a restriction to each element of the domain. Only one thing can be assigned. How can we tell if a relation is a function or not? By the way, we need the word relation because we cannot just go around saying a function that fails to be a function. That's a little weird. So a thing that fails to be a function is still a relation. How can we tell if a relation is a function or not? Well, it depends what is given. If the equation is given and if the graph is given. All right, I'm going to draw a few graphs and you tell me which one is a function or which ones are. Okay. So how can you tell if a relation is a function given the graph? Well, what can go wrong? Algebraically, what can go wrong is one element of the domain with two different assignments. That would be one x value with two different points. You see, this here, one x with two different y's, this is not a function. Just one point is enough to mess it up. Not a function. Because you can find basically a vertical line that intersects the graph more than once. That means that is not the graph of a function. That is just a relation, not a function. And this is called the vertical line test. Now here, imagine that you're a big photocopier and you scan left to right with a vertical line. You're never going to intersect this graph more than once. This is a function. But I put a point here and that's it. Because now there is one vertical line with two intersections with the graph. Function. And this one again is barely not a function. Well, I guess if you're that rusty, then we should spell out the whole thing. This is called the vertical line test. The graph of a relation depicts a function. So the relation is a function if all vertical lines intersect the graph. But there are two options. Not at all or just once. So at most once. You can have a small, cute little domain here. This one, see, that's not a problem. It's just two or more intersection with the graph would be a problem. So that's the vertical line test. That's how you test if a graph belongs to a function. Now I kind of want to show you not the equation yet, but there is another more basic thing that I'm not sure anymore. We should skip. And that is when you have these, I don't know, pictures. Here's the domain, here's the range. Okay, is the first one a function? You can have a set where you list one with A, one with B. This is just another way of representing the same thing. each arrow becomes point, an ordered pair of numbers. Is this or this, is this a function? Yes or no? And
No.
if yes, why not? No, because one is misbehaving. That is not allowed, right? There are multiple values assigned to one. The same way to see it from this is you have two ordered pairs where one is the first number and the second number or letter is not the same. That means to one, we assign both A and B. That's a no-no. And this one usually confuses students because they think this is not a function. It's a boring one, but it's a function. It's a constant function. That's what it is. Because from each number in the domain, just one thing comes out. This branching is okay. You can have, you know what I compare this? Imagine that the domain is time, I don't know, measured in seconds, and the range is -10 to 30, where these are floors of a high rise with the garage, the deep under garage, floors of a high rise. And that's why we model the motion of the elevator. And if the elevator is at motion, we wait until it stops, and that's going to be the assignment. So if it's so L of 0 equals 5 means what? Describe what this means here. L of 3 equals 5. After 0 seconds, the elevator is on the 5th floor. That's what it means. After 3 seconds, the elevator is on the 5th floor. This elevator is sitting on the 5th floor. Maybe traffic is slow. No one is going anywhere, right? That's okay. What I would never wanna stand in an elevator that does this. What's with that elevator? Fell apart, right? Because at the same time, it's at both locations. I just wanna kind of give you an instinct, like, this is okay. Different times, one location, it could be the same or different, but it doesn't matter. But at one time, you should not have two locations, right? That's physically scary. I would not want to stand in an elevator that does this. This is okay, because this is this kind of branching. Now, this is not okay, because to the number 2 in the domain, we assign two different numbers. So after 2 seconds, the elevator is at least at two places, on floor 12 and floor -7. That's probably not a good thing. So we're still talking about how can we tell if a relation is a function or not. From the little picture, from the graph, and now from the equation. If it's in the form of f of x equals 3x minus 5 squared plus 1, or y equals 3x minus 5 squared plus 1, it is a function. Because there is a unique recipe as to how to get y in terms of x. 1x, no matter what your number is, you triple it, you get a number. You subtract 5, you get a number, you square it, you add 1. If you take the same number over and over, you're going to keep getting the same y value. So there is a unique recipe to compute y in terms of x. Now let's just do the unit circle. X squared plus y squared equals 1. If we try to solve for y, what we're going to get is y squared is 1 minus x squared. And then you have to be able to solve this correctly. That means y is not just square root of 1 minus x squared, but plus or minus. And that here is what it's telling you. This is not a function. It will fail the vertical line test because this unit circle, this here is the upper half. This is f of x equals square root of 1 minus x squared. By the way, you have to be, this hurts people in calculus big time, that I give them this function and it's not a parabola. Just rewrite it as y squared both sides. You're right here is the unit circle. Well, the upper half of it. And this here is the lower half. This is g of x equals minus square root of 1 minus x. Okay, so being able to bring circles into function form is going to be pretty important in calculus. But you see, this here tells you there is not a unique recipe to compute y given x. And if it's already solved for y and you don't see a plus minus, then it's pretty much a function. So if it's already in this nice function form, that's a function. But also for calculus, you might get it on day one graph, y equals square root of 9 minus x squared. Or versus they will say f of x instead of y. Just dump f of x, switch to y, square both sides, y squared equals 9 minus x squared plus y squared equals to 9. That's a circle. And this is the upper half of it. The radius is 3. So I'll try to put it in the homework for you to understand. To be able to go back and forth between. This is very typical to relations because you cannot solve uniquely. Sometimes you cannot even solve for it, let alone uniquely. If it's degree 3, 4, swimming in variables. This one is simple enough that you can solve. There is one more definition. A function is one-to-one, or I really like this word, injective, same thing as one-to-one. If for all x1, x2 in the domain, if x1 and x2 are different, then the function values assigned to them are also different. That's basically ruling out this sort of branching. This here is a function, but not one-to-one, because in a one-to-one function, you can sort of pair up the x and y, and everyone has their own, sort of like married couples. That's not clearly not the case here. This is a function, but not one-to-one. A one-to-one function, well, after you might rearrange things, looks like this. 1-to-1. You can pair them up in a, also called a bijection. It's an injection on both ways. Bijection. Now, this is what the one-to-one function is. Yeah, there is an alternative way, logically equivalent way of stating it, but it's important enough for you to hear both. And that is, it's an alternative definition of one-to-one. This says if x and y, if x1 and x2 are different, then the function values are different. If you start different, you land different. And the other way to say that it's one-to-one, that if you take a function value of x1 and x2 and you land on the same thing, then x1 and x2 are already equal. You can't do this. So under a one-to-one function, if you're landing at the same place, you already started at the same place. So f is one-to-one. If roll x1, x2 in the domain, if f of x1 equals to f of x2, two function values are the same, then they must have started the same. Then x1 equals to x. So this says different x means different y. So if you get the same y, you must have the same x. It's different x, that's different y. This is logically equivalent, but both forms are pretty important. All right, so I'm going to draw two pictures of functions. I'm going to tell you a secret. There is a formula, but I'm not telling you. The formula is triple and subtract 1. So 2. Triple and subtract 1. 5, right? 5. Triple and subtract 1. 14. Triple and subtract 1. Oh, 1. Triple and subtract 1. That's 2. All right. And let's call this f. So it's a secret, but f of x equals 3x minus 1. And very small domain. Tiny domain. Maybe we will need some more, but and g is just going to be the square function. -2 -1 0 1 2 4 1 0. So there's no way to do this nicely. -2 squares to 4. This is just going to be g of x equals x. They're both functions. The big difference is this is 1 to 1. This isn't. You see, -2 and 2 will have the same function value. All right. So now the definition is so simple, and just so many things pop out of that definition. Given a function f, the inverse relation is what we get when we literally reverse the assignment arrows. So we use the same line, but the arrow will point a different way by reversing. So that means that in the inverse relation, the range, what used to be the range is now the domain, what used to be the domain is now the range. And I have issues, serious issues with the notation. It's not very clear, but oh well. So we just literally take this little tick and put it there, and that's it. But everything is gonna sort of, there is a role reversal. What used to be x is now y, what used to be y is now x, what used to be domain is now range. But it's pretty much the same assignment. Well, we reverse it. Okay, now notation. Don't like it. Don't like it at all. F inverse. My issue is that it's too ambiguous in the sense that some people think it's 1 over, that it's an exponent. So given the first picture, f of 2 equals 5 is the same thing as f inverse of 5 is 2. Maybe I should have used that one, right? So the inverse function, no, the inverse relation of f assigns to 5 the number 2. F of 5 is 14. That can be turned around and as the inverse image of 14 is 5. F of 1 is 2, so the inverse image of 2 is 1. Now, what if you want to say reciprocal? Notice the difference. F inverse of 5 and f of 5. Look at the location of the negative one. Again, I don't like it. I think this needs to be changed. It's way too ambiguous. This is inverse function. So this is 2. This is 2. This is inverse relation. Inverse relation. And this is exponent. So given this picture, and I carefully put 5 in both places, this is 1 over 14. You see that? We apply the function forward, and when we're done, we take the recipe. And then, just for kicks and giggles, I don't know in what order, but what is this number? Terrible. Terrible. What is this? Given this picture, what is this number? I guess I should state that it should be this. Well, inside the parenthesis is inverse relation. So you start with 5 backwards and you go to 2. And then now that one is an exponent, so it's 1 over 2. But as I said, don't like it at all because it's too ambiguous. It's too close. Now in trigonometry, and in calculus, it's a major felony to mistake one for the other. And for example, we have notation for both. So for something like this is inverse sign, not reciprocal. You're gonna see arc sign. These two are the same, and this is inverse. And 1 over sine x, well, that has a name. That's cosecant x, right? So you're gonna be yelled at if you see this and the next line you're gonna go 1 over sine x. No, if you must know that's sine x, the location of the -1 has to be But again, you're going to see in this course, you're going to see cosecant x for the reciprocal and arcsine x for the inverse relation when you reverse the arrows. So we're going to avoid in both forms of that ambiguity. I'm pretty sure that these names and this notation had to do with this ambiguity. When you have another teacher, not me, and they say inverse, they mean inverse function, not inverse relation. They should be a little bit more precise, and they should say inverse function. But basically, mathematicians dig functions, inverse functions, not relation. They want inverse functions. Why? Because operations. If you perform an operation, you want one result, not two or three. So let me just say that mathematicians dig inverse functions. Mathematicians like when the inverse relation turns out to be a function. So mathematicians like when the inverse relation turns out to be a function. Visualizing these two basic cases, the inverse, in which case it's a function, in which case it isn't the inverse relation, and why do you think, what makes the difference? So when is f inverse a function? Because mathematicians like that. What is the property of f that will guarantee that the inverse relation will also be automatically a function? Okay, so one thing at a time. These red arrows show you a function, right? Just one thing sticking out from each. But this one isn't a function because look at 4. When we reverse the assignment, 4 will point towards -2 and 2. So the inverse relation assigns both 2 and -2 to 4. Why is that? What property of the forward function does this? Why does this not happen here? Why does it happen here?
Because the first one is a one-to-one function.
Exactly. One-to-one functions, they are automatically, the inverse relation is a function because it's basically they're paired up. So it's easy to travel back and forth between these, right? But the minute you have this branching backwards, there is trouble, right? So one-to-one functions are also called invertible because their inverse relation is automatically a function. F inverse. And when mathematicians write this down, they already think function. But I'm just going to say the inverse relation is a function if and only f is 1-to-1. Okay. There are going to be, again, 3 things. I'm just trying, I don't know how much I can squeeze into this class. So let's first graph the inverse relation because that's fun. So there are 3 ways to do that, but I think I'm not going to show you all 3. My recommendation is plot, swap coordinates, connect the dots. I'm just going to use x squared, which is g of x. So g of x was x squared. And let's say the domain is all real numbers. So if 2, 4 is on the graph of a function, that means that to the number 2, we assign the number 4. Reverse that assignment is the same as swapping the 2. X becomes y becomes x, right? So that will become 4, 2. Now, 1, 1 will not feel a thing when you swap the 2 coordinates, and neither will 0, 0. Right? But in between here, you will feel the difference because if x is half, y is a quarter. So you have a point that's, if x is half, y is a quarter. So on the inverse, it's going to be quarter half. It's going to be something like that. And so basically, you should have enough points to be able to, this is clearly not enough, not a lot of points. Keep going, 3, 9, that will become 9, 3. 3, 9, 9, 3. And things that you can describe like, oh, it's just pretty steep as it keeps going up, make up along the y-axis. That's going to become along the x-axis. So everything x becomes y, everything y becomes x. What you're going to get is this. And you could say, oh, big mess. You could say, one is on both the forward and the backward function, right? You could say, wait a minute, this looks a whole lot like the square root function. Yeah, right? If 2 squares to 4, the square root of 4 is 2, except we're not done. Because there is a point that is -1 for x, 1 for y. Swap the two coordinates, and we're going to get one -1. And then -2, 4 will become 4, -2. And it's a common mistake for people to think that, oh, so it's a 90-degree rotation. That's not what happens, because this piece became this piece, and this piece became that piece. You know what it is? It's a reflection to this diagonal line y equals x. But I think that's much harder to do. To reflect to a line is hard enough, but to a diagonal line, to this day, when I graph the inverse, I do this, plot a lot of points, swap the coordinates, connect the dots, and then I use the symmetry to check. There should be always a reflective symmetry to this line y equals x, which is an interesting thing that happens. So it's a reflection. This point got there, that point got there, this point got there, and so on. So now we're ready to graph the inverse relation for the trigonometric functions. Basically, just graph the forward one, swap coordinates in enough points, and then connect the dots. And, you know, sine x and all trigonometric functions are very badly not one-to-one. The whole thing repeats, right? Not only not every x gets different y, just copy and paste, copy and paste, copy and paste. And so the trigonometric functions, all of them are very badly not one-to-one, which means the inverse relation is going to be very badly not a function. They're going to be relations. And, you know, sine x and cosine x sort of wraps itself around the x-axis. The inverse will wrap itself around the y-axis. It's kind of cute. So let's do the inverse relation. It's not going to be 4 sine x. 4 sine x, which I'm going to refer to as r sine. No, I don't even know, because the notation usually suggests it's already a function, and that's not what we're talking about. So it's just going to be the inverse relation for sine x. So I would plot a lot of points with their coordinates and then swap them. 0, 0 will not feel a thing, but I promise that's going to be the only thing. Now, what about this point? The coordinates are pi over 2, 1, and it's important. Pi over 2 is like 1.5. So it's more. This is longer than this. Swap the coordinates. What do we get? We get 1 pi over 2. 1 pi over 2. And you can have points intermediate mediate between these two, but also think of the symmetry. That's the symmetry line. So we should get something like this. And this is where it matters that sine x is not that tall and skinny. These two never bite into each other. They don't meet, only at the origin. So if they were taller, then they would kind of hook into each other, but that doesn't happen. And then this point here is pi 0. And that's going to be in the inverse, it's going to be
0 pi.
0. Mm-hmm. And so just swap 0 pi. And so, and you can, I use the symmetry to check if I'm at the right track. And then what about this point here? What are the two coordinates? Swap them. What does it give us on the inverse relation? This is point, this is 3 pi over 2, -1. So swap it. The inverse is going to be -1, 3 pi over 2. It's pi over 2 pi, a little closer. Oh, and if they ask domain range, you literally swap them. Now, the domain is going to be between -1 and 1, right? And the range is going to be everything. Sine x the domain is for real number, and the range is -1, 1. Literally swap those two. The domain becomes the range becomes the domain. So the inverse relation, the domain is what the range used to be, -1, 1, and the range is everything. And you probably can see that, oh, so this is going on here, -pi over -1 is going to be -1 minus pi over 2, of course. And if the original function wraps itself around the x-axis, this is going to wrap itself around the y-axis. Now this is clearly very badly not a function, right? Now I want to assume that you're going to sit down and do the inverse relation, the picture of the other guys, at least cosine and tangent. You should try secant, cosecant. All these vertical curves will have to become horizontal curves. Oh, actually, I told you that there are 3 ways to graph the inverse relation, right? Number 1, I think it should be your first method, swap coordinates, connect the dots. Number 2, reflect to this line, but that's kind of hard. Even I don't do it. But when I was a student, I said, wait a minute, can I just not, where is the coordinate system? Okay, so I'm gonna graph, I don't know, I've never done this. Don't worry about the numbers, just the direction. So I'm gonna graph sine x here, something like that. And so when I was a student, I was like, but can I just not rotate my paper so that x is where y used to be and y is where x used to be? Then I would be looking at the inverse, right? So here is sine x, and can I rotate my paper so that x is that? If I rotate this paper into a position where this says y and this says x, I'm looking at the inverse. But the problem is, if I rotate my paper 90 degrees, then yeah, this should be y, but this should be on the other side, right? The technique still works if you look at it from behind. If you, I don't know how this would work. If you look from behind, let me just make it really loud here so it pushes. If you look at it from backwards, I was proud of that as a student. I came up with this. Now this shows y, right? Well, it's written this way, and this shows x, and x is where y should be, y is where x should be, and there is the inverse sign, right? You have seen it before. So sadly, with this technique, you cannot see the forward and the backwards thing at the same time. So we're not going to do the other two. I'd rather tell you what we do because we insist on inverse functions. And the inverse trigonometric functions, not relations, are actually very, very important in calculus. If you have to take Calc 2, you're going to need the inverse trigonometric functions are huge. What do mathematicians do when they want inverse function and the function, the forward one, is not one-to-one? They still want function. Now I got good news and bad news. The bad news is this is a part of mathematics that you're going to have to memorize. The good news is that the decisions that were made without asking us are pretty reasonable. For example, here is our x squared, and here is our inverse. This fails the vertical line test. Guess what? One-to-oneness can be tested with a horizontal line test. So, but we want an inverse function because we want inverse operation, namely we want to take square roots. So if f is not one-to-one, what's the issue? There are 2 different x values or more, 2 or more x values with the same y values. So then throw out the extra one. So basically, if f is not one-to-one, we restrict its domain so that it is one-to-one. And it's probably the biggest one we can keep, and it is one-to-one. So we restrict its domain so it is one-to-one. So this is step 1. This we call g of x equals x squared and the inverse relation. A number and its opposite square to the same thing. So the bad news is we have to memorize how mathematicians decided to agree to restrict the domain. But guess what? We tossed out the negative part. So basically, the restricted domain is just 0 and the positive parts, and the range is pretty much the same. So we have this, and now when we take the inverse, it's a function. And it's the square root function because we want an inverse operation and we want to be able to take square roots. But that's how it goes. And it's easy to remember to toss out the negative numbers. But if you think about trigonometry, there's just this, it's going to take a little bit of memorizing. All you got to memorize is how the restrictions were done. And then we swap the domain with the range, we swap the coordinates. The rest is easy, and there is no computation. It's just this story and this drawing that I'm showing. So we have still more to learn about generally inverse functions, but we started inverse trig functions as well. So I think we'll be able to wrap it up on Thursday. So I'll stop here. Thank you guys, and I'll see you on Thursday.